During the third laboratory of Chemistry 182, students were challenged to create alum crystals. The video you are about to watch is the first in a series of 3 which show the struggles that my partner and I endured during our quest to create the best alum crystals. Before we could create alum crystals, first we had to create just regular alum. We did this by starting out with just pure aluminum and dissolving it in potassium hydroxide. This reaction created aluminum hydroxide ions and released hydrogen gas. After this first step, the solid impurities were then filtered out. During the second step, sulfuric acid was added to this solution. This created solid aluminum hydroxide, which precipitated out. After that, we added more sulfuric acid, which neutralized the aluminum hydroxide, causing it to form aluminum ions and forcing the aluminum hydroxide to dissolve within the solution. While in the original procedure, the adding of the sulfuric acid was split into 2 different steps, in our own personal procedure, we morphed it into one big step, while all the sulfuric acid was added to the solution and then incorporated using a stir bar and heat to speed up the reaction. After all of the aluminum hydroxide had dissolved within the solution was set aside for it to cool down. After it had cooled down, it was added to an ice bath. This cooling of the solution helped to precipitate out the alum. After the creation of the alum, it was time to make the actual alum crystals. Based on the temperature of the water, a specific amount of alum was added to 40 milliliters of water. This amount of alum was chosen based on a solubility table. For our own personal procedure, we used 20 degrees Celsius, which is about room temperature. While the original amount of alum that was added to the solution was based off of the solubility table, we continued to add alum until the solution was completely saturated, meaning that the solid would no longer dissolve within the solution. After the solution was saturated, the excess solid was filtered out. Then, the solution was separated into 2 different vials, one for my partner and one for me. The crystals are currently sitting in uncapped vials so that the water can evaporate out around the alum. This slow, undisturbed process of evaporation means that the alum can bond to itself very slowly, giving it the time to create very organized and geometric patterns and, eventually, very pretty crystals. Now, I know everyone's dying to know what our own personal crystals look like, so we'll show you a little picture. And, yeah. As you can see, there's literally nothing in either of these vials. Now, I know that the rubric wanted us to talk about the size and shape and number of the crystals, so the size is very, very, very small, can't even be seen by the human eye. Shape? Who knows? I can't see it. And number? 0? I mean, there's definitely some there, but 0 are visible. Now, I know what you're all thinking back home. Catherine, you're telling us all about how to create alum crystals, but how do I create regular table salt crystals? Well, I'm glad you asked. Creating table salt crystals is very similar to creating alum crystals. In order to grow sodium chloride, one must first make a saturated solution of salt by boiling water and adding table salt into it until the salt stops dissolving within the solution, showing that it's saturated. After that's done, filter out the extra salt and place the solution within a clear jar. Then, wait for the water to evaporate around it, much like with the alum crystals. Eventually, crystals will form at the bottom of the jar. Now, that might be enough information on how to make crystals for most of the kids back home, but I know there are a few of you clever little chemists who want to know a little bit more about how to make crystals. So for all of you, I'm going to tell you about a little process I like to call vapor diffusion. Everyone else actually likes to call it vapor diffusion as well. That's just the name of the process. Okay. For vapor diffusion to work properly, you need a binary solvent system. In order to create a binary solvent system, you need to choose 2 liquids that mix together well. Your compound that you're trying to make the crystals with should be soluble relatively well in the liquid with the higher boiling point. We will now call this liquid the solvent. The compound should also be insoluble in the liquid with the lower boiling point, which will be called the precipitant from here on out. You want to prepare a solution using the solvent and the compound and place it in a small, open container. You then want to put this container inside of a larger container which contains some of the precipitant. You then want to heat the entire apparatus to a temperature that's above the boiling point of the precipitant but below the boiling point of the solvent. This heating will turn the precipitant, which is more volatile, into a gas, which will diffuse over the solvent, leading to oversaturation, nucleation, and, if everything goes well, crystallization. Now, I'm sure you're all thinking that this whole process seems a lot more difficult than the whole evaporation process that we've been talking about thus far. And that's true, it's not even close to as simple. And also, it's very, very hard to find two suitable solvents which mix together well. However, it works very, very well in small amounts, usually gives pretty good crystals, and if you can find two suitable solvents, the parameters are incredibly easy to control. And, well, that concludes this video. At least the first of 3. Tune in next week where we go back to the alum crystals to see if you can see them now with the naked eye.